Welcome back to the wonderful world of physics. This is chapter 21 on Gauss's law, the homework solutions. We'll start with number 21. It says, what is the electric field strength in a region where the flux through a 1 centimeter by 1 centimeter flat surface is 65 Newton meters squared per coulomb if the field is uniform and the surface is at right angles to the field? All right, so we have those 90-degree angles. Flux is electric field times area. We don't have to mess around with the integral or the dot product. It all simplifies with a uniform electric field just to this. Electric field strength times the area. So the electric field is the flux divided by the area. So we have 65 Newton meters squared per coulomb divided by 10 to the negative 2 meters squared. That's the area. And we get 6.5 times 10 to the 5th newtons per coulomb. Number 22. A flat surface with area 0.14 meters squared lies in the xy plane in a uniform electric field that is 5.1 I hat, 2.1 j hat, and 3.5 k hat kilonewtons per coulomb. Find the flux through the surface. Okay, let's be mindful that it was given in kilonewtons per coulomb. Helpful to draw a picture. So in the xy plane, and we have the area vector, and I've drawn it coming out of the page. And so there is area vector is 0.14 meters squared k hat. And here I've written out the electric field as a vector. Flux is the dot product of the E vector and the A vector. So I've written them out, and remember the dot product between two vectors is the product of the x components plus the product of the y components plus the product of the z components. So for the x's we have 5.1 times 0, and there's our 0. For the y's 2.1 times 0, and there's our 0. For the z's 3.5 times 0.14. Now we need to take note of the units, and so I've written in kilonewtons per coulomb times meters squared. So we multiply the 3.5 times 0.14 and we get 0.49, and the units are kilonewtons meters squared per coulomb, and let's turn those into MKS units, so Newton meters squared per coulomb. So instead of 0.49, it's 490 Newton meters squared per coulomb. Number 24. A sock comes out of the dryer with 1 trillion excess electrons. What is the electric flux through a surface surrounding the sock? All right, so here I've drawn a sock and a surface surrounding it. And I've drawn these electric field lines. They are going in to it because the sock has negative charge with all those electrons, so the electric field lines go in. And the question is asking, what is the flux through that surface? So flux is equal to, by Gauss's law, the charge enclosed divided by epsilon naught. And so 1 trillion electrons times 1.602 times 10 to the negative 19 coulombs per electron, and we'll divide by epsilon naught, that permittivity constant that is 8.85 times 10 to the negative 12, and we get 1.81 times 10 to the 4th, and flux is Newton meters squared per coulomb, and you can see that if you go through the units in the previous line. Number 25. What is the electric flux through the closed surfaces marked A, B, C, and D in the picture? I have not shown the picture here, but hopefully you can see it in the book. And for surface A, now surface A, as I'm looking at the picture, encloses two charges. One of them is a plus Q, the other is a negative 2Q. The sum of those is negative Q divided by epsilon naught. So there's the answer. The total charge is negative Q, and then we're going to divide by epsilon naught to get the flux. For surface B, as I look at the picture for surface B, it is the entire surface. And so we add up, there's a Q, there's a negative 2Q, there's a negative Q, there's a 3Q, there's a negative 3Q. And when you add all of those together, you get negative 2Q. So the flux is negative 2Q divided by epsilon naught through surface B. Surface C has no charges enclosed, so by Gauss's law, the flux is going to be 0 divided by epsilon naught, or just 0. And surface D has a 3Q and a negative 3Q. Those add together to make 0 divided by epsilon naught, and it gives 0 flux. Number 26, a 6.8 microcoulomb charge and a negative 4.7 microcoulomb charge are inside an uncharged sphere. What's the electric flux through the sphere? The flux is going to be, by Gauss's law, the total charge enclosed divided by epsilon naught. So we add those two charges, the 6.8 plus negative 4.7, and we get 2.1 microcoulombs. Let's call that 2.1 times 10 to the negative 6 coulombs. We're going to divide by the permittivity constant, 8.85 times 10 to the negative 12, and we get a flux of 2.4 times 10 to the 5th Newton meters squared per coulomb. Notice that it didn't matter in this question that it was a sphere. Just like in the previous questions, number 25 and number 24 with the sock, the shape didn't really matter. All that matters by Gauss's law, if we want to know the flux, it's the enclosed charge divided by epsilon naught. Number 27. A 2.6 microcoulomb charge is at the center of a cube 7.5 centimeters on each side. What is the electric flux through one face of the cube? Hint, think about symmetry and don't do an integral. Well, if you look at the picture, the electric field lines are going out in all directions, and the question is asking, what is the flux through one face of the cube? Now, one face of the cube is one of 6 possible ways that the electric field can get to the outside, and so it's going to be 1/6 of the total flux. So here I've written the flux through one face is 1/6 of the total flux. And so let's do that. 1/6 times the charge enclosed divided by epsilon naught. The charge enclosed is 2.6 times 10 to the negative 6 coulombs. We'll divide by epsilon naught. Don't forget to take your 1/6. And the answer is 4.9 times 10 to the 4th Newton meters squared per coulomb. Number 29. A solid sphere 25 centimeters in radius carries 14 microcoulombs distributed uniformly throughout its volume. Find the electric field strength 15 centimeters, 25 centimeters, and 50 centimeters from its center. All right, so you can see I've written down the given information here, radius and charge. It's a solid sphere. And parts A, B, and C, we want to distinguish between, is this going to be inside the sphere, on the surface, or outside the sphere? So with a radius of 25 centimeters, part A, 15 centimeters, that's inside the sphere. Part B, 25 centimeters, that's on the surface of the sphere. And part C, 50 centimeters, is going to be outside the sphere. So let's look at part A, the condition where we're inside the sphere, at a position where some of the charge is within where we're at, within that 15 centimeters, yet some of the charge is still beyond it. And I'm not going to go through it all again, but you can refer to in the book example 21.3, where they show that the charge enclosed, if you're looking at a spherical surface within a solid sphere, the spherical surface having radius little r, the solid sphere having radius big R. The charge enclosed is related to the ratio of the volumes of those spheres, and that is going to be little r cubed over big R cubed times the entire charge. So if you don't understand where that comes from, I encourage you to look back in the book or in my notes at example 21.3. All right, so let's think about Gauss's law, the flux, and we'll insert this here for a sphere. is going to be, for a spherical surface, 4 pi little r squared times electric field. And that equals the charge enclosed divided by epsilon naught. So the charge enclosed being r cubed over big R cubed times q. And so we're going to take this and we're going to solve it for E. E is q little r divided by 4 pi epsilon naught r cubed. When we plug in all the values, make sure that you'd use MKS units. So turn those microcoulombs into 14 times 10 to the negative 6 coulombs. Turn those centimeters into meters. And you get 1.2 times 10 to the 6 newtons per coulomb for part A. For part B, the condition where we're looking at it on the surface, we're going to, we can apply what we did in part A, apply the same thing, and it works as well. So 2 times 10 to the 6 newtons per coulomb. So in this case, little r and big R are both 0.25 meters. Or for part B, we can use a solution, this is actually preferable, but the solution that I'm about to do for part C. It'll work also. So let's go down to part C, outside the sphere. We have the same thing. Gauss's law says that the flux is through a spherical surface 4 pi little r squared E, and that's going to equal the charge enclosed over epsilon naught. Now, the charge enclosed is the entire charge of the sphere because we have gone beyond the sphere. So we get that E is q over 4 pi epsilon naught little r squared. And notice what I've written here in green. This is the same as what we learned in an earlier chapter. The electric field from a point charge is k times the charge divided by distance squared. And a big idea that we learned in this chapter is that if we are beyond a charged sphere, looking at a place beyond a charged sphere, you can treat that sphere as if it were just a point charge. Now, let's go back up to part B. I said, or you can use the solution to part C. Well, just look what I've done here in the green. If we're on the surface of the sphere, we can also treat that sphere as if it's a point charge. K times q over r squared, and its charge over 4 pi epsilon naught r squared. If you go back to the top, this is how I showed you to solve for part B. Notice that since the r's, the little r and the big R are equal to each other, little r over big R cubed just becomes big R cubed, becomes r squared on the bottom. And that's the solution to part C. So however you do, well, actually there's only one way to do part C. The answer here, when we plug in r equals 0.5 meters, we get 5 times 10 to the 5th newtons per coulomb. Number 32. An electron close to a large flat sheet of charge is repelled from the sheet with a 1.8 piconewton force. Find the surface charge density on the sheet. All right, here I've drawn our big sheet. The electron is being repelled. That means that the electric field is going into it. And so we can say the electric charge on the sheet is negative. And what we learned in this chapter, that for a large flat sheet, it was actually an example where we did an infinitely large sheet, electric field is sigma, which is the surface charge density, divided by 2 epsilon naught. We're also going to need the relationship that the force on a charge is the charge times the electric field. So let's apply that equation, force equals charge times electric field. So we have negative of the elementary charge, that's the electron, times the electric field. And now I'm going to replace for electric field sigma over 2 epsilon naught. So the force is negative E sigma over 2 epsilon naught. Now, you could do this problem without those negative signs. The negative sign is me being careful that the electron has a negative charge. If you're only concerned with magnitudes, then you can probably get away with ditching that negative sign. But we just have to realize at some point that negative sign is important because ultimately, if you just think about the picture, if it's repelling an electron, then it is negative. So at some point that negative sign has to come up, so I've just thrown it in there from the beginning. We solve for sigma, 2 times F times epsilon naught over negative little e. So here we have 2 times 1.8 times 10 to the negative 12 newtons times our permittivity constant divided by negative 1.602 times 10 to the negative 19 coulombs. And we get that sigma is negative 1.99 times 10 to the negative 4 coulombs per meter squared. And again, that's that sigma, the surface charge density. It refers to how much charge is in a given area. Number 43, time for a little bit of calculus. An electric field is given by E vector is E naught times y over a k hat, where E naught and a are constants. Find the flux through the square in the xy plane bounded by the points, and it's basically a square that starts at the origin that goes out to AA. All right, so we want to think how we're going to do this. I've written off in purple just to have a sense of what is the electric field exactly doing here. Well, it starts off, I've written the vector up at the top, and it starts off where y is equal to 0. That makes the entire electric field 0. And it goes all the way up to y equal to a. That means E naught times a over a. So up at the top, it's E naught. So we're looking at an electric field that is gradually growing from 0 up to E naught. And let's see, let's start by doing the integral. Actually, drawing a picture is a good idea. Because the electric field is changing with y. Y is going to be the spatial dimension that we're going to want to integrate over. So here I've laid out a strip, an infinitesimally small, thin strip that is a thickness of dy and a length of a. All right, let's go to the integral. Flux is the integral of E dotted with dA. And so that is going to be the magnitude of E times the magnitude of dA. And there is a cosine theta component, but area sticks out of the page. The area vector comes out of the page. Or maybe it goes into the page. Not quite sure. It can go either direction. And the E vector with which area is being dotted also comes out of the page. So that's going to be if they're going in the same direction, meaning they're both coming out of the page, then that cosine component is going to be 1. However, if as E is coming out of the page, maybe the area vector is pointing right into the page, then that's going to be -1. So that's where this plus or minus that I've written comes from. So the magnitude of E is E naught y over a. The magnitude of dA, that strip area, is a times dy, and the cosine component makes it a plus or minus. All right, let's take that integral. What goes to the outside? The a's divide out. The plus or minus E naught goes to the outside, and we're left with the integral of y dy. We want to know the limits of the integration, so we just go over to the picture and we see what are the limits of y? Well, it starts from 0 and it goes up to a, so there's my limits of integration. Take that integral, so we have plus or minus E naught and then times 1/2 of y squared from 0 to a. And in the end, you get plus or minus 1/2 E naught a squared. And again, the plus or minus just means it might be going in, it might be coming out, relative to which way we refer to in and out as part of the surface. But if you're just interested in the magnitude, you can just say 1/2 E naught a squared. Number 45, a biology application. It says a study shows that mammalian red blood cells, RBCs, carry electric charge resulting from 4.4 million in rabbit cells to 15 million in human cells. Excess electrons spread over their surfaces. Approximating rabbit and human RBCs as spheres with radii 30 micrometers and 36 micrometers respectively, find the electric field strengths at the cell's surfaces. All right, so we have basically two separate problems here. One is for the rabbit cells, the other is for the human cells. And here I've listed out the given information. And it says to approximate them as spheres. Okay, so we're going to use Gauss's law. Flux, which for a sphere is going through a spherical surface, is 4 pi r squared E. That equals the charge enclosed divided by epsilon naught. So we're going to solve for the electric field. That becomes the charge over 4 pi r squared epsilon naught. And then we're going to solve for the charge. So with the rabbit cells, the charge is, we have 4.4 million times the that many, this much coulombs for an electron. And we're going to use that radius is 30 times 10 to the negative 6 meters. So we're going to plug in what we get for charge here, what we get for the radius, and you should get an electric field of 7 times 10 to the 6 newtons per coulomb. For part B, with the human cells, you can get the charge, 15 million electrons, as you see that I've done here. Multiply those out. The radius is 36 times 10 to the negative 6 meters. So we're going to take that charge, we're going to take that radius, we're going to plug it in to the electric field equation up here where my red pointer is, and you should get 1.7 times 10 to the 7th newtons per coulomb as the electric field. Number 47 says a solid sphere 2 centimeters in radius carries a uniform volume charge density. The electric field 1 centimeter from the sphere's center has magnitude 39 kilonewtons per coulomb. Question A, at what other distance does the field have this magnitude? Question B, what is the net charge on the sphere? All right, so let's assess what we're looking for. We have a solid sphere with uniform charge density. At 1 centimeter on the inside, electric field is 39 kilonewtons per coulomb. We want to know at what other distance is electric field 39 kilonewtons per coulomb. Well, if you think about the relationship, and we saw this in the example where we looked at a solid sphere, this is what happens to electric field, and here is the radius of the sphere. It increases linearly, and then inside the sphere, and then it's going to decrease non-linearly. So we're dealing with R1 at 1 centimeter. The electric field is up here, and then it's asking where is it going to be here, and you can see on the graph right about here, something beyond R. So that's the answer, that's the ballpark of the answer we're looking for. Now, inside the sphere, you can refer, I already derived this, refer back to problem number 29 to see where I got this from. The electric field is Q times R1 divided by 4 pi epsilon naught times the radius of the sphere cubed. This is a unique solution. Outside the sphere, the electric field is, we treat it like a point charge. Charge over 4 pi epsilon naught R2 squared, or we could just say KQ over R2 squared. And we're looking for where those electric fields are equal, so let's set these two terms equal to each other. We set them equal to each other, and you can see algebraically a whole lot of stuff divides out. The charge divides out. 4 pi epsilon naught divides out. And what we're left with after everything's divided out is R1 over big R cubed equals 1 over R2 squared. And our job is to solve for R2. So go through the algebra. R2 is the square root of R cubed over little r1. Plug in those values. We have 2 centimeters cubed over 1 centimeter and the square root of that. So we get 2.83 centimeters. And now question B is asking what is the net charge on the sphere given this information. So if E is the electric field is Q times R1 over 4 pi epsilon naught big R cubed, we can just solve that for Q. So we get 4 pi times epsilon naught times the radius, which is 0.02 meters, we're going to cube that, times the electric field, which is at R1, which was 1 centimeter, 39 kilonewtons per coulomb, and then divide by R1, which is 1 centimeter, but we need to make it meters, so 0.01 meters, and we get 3.5 times 10 to the negative 9 coulombs, or 3.5 nanocoulombs. And that is the end of the chapter 21 homework. I hope you have a great day.